These four series are all conditionally convergent. Let me explain why. Starting from the first one, so we have the sum, n goes from 1 to infinity. The top we have an alternating term, the bottom we have n plus 3. So since this is an alternating series, we have to use the alternating series test. So the Bn is equals to 1 divided by n plus 3. In case you don't remember, the given is called An. We use a Bn to take away the alternating term. And then the next term is 1 divided by n plus 1 plus 3. So 3 plus 1 is equals to 4. So for alternating series tests, first we have to show that the next term is less than or equal to the current term. When n is equals to 1, we have 1/5 less than or equal to 1/4. When n is equals to 2, we have 1/6 less than or equal to 1/5. So number 1 is true. Number 2, we have to show that the limit of Bn is equals to 0 as n approaches to infinity. So first of all, we have a limit as n approaches to infinity of 1 divided by n plus 3. Then we have 1 over infinity that is equals to 0. So the series is convergent by the alternating series test. All right. So at this point, we say that the series is convergent. How do you get a conditionally convergence? Conditionally convergence is if you take a look at the absolute value, you will end up with a conclusion of divergence. So let's take a look at that. So first, we take the absolute value of An, right? So the absolute value of An, that is the sum of the absolute value of negative n raised to the n plus 1 divided by n plus 3. So after taking the absolute value, we can just remove the alternating term, right? So now we only have 1 divided by n plus 3. And then this one, we can use a comparison test. So for comparison test, what is your An and what is your Bn? The An is always the given series, 1 divided by n plus 3. And then for the Bn, so here is the logic. As n goes really, really big, we don't need to worry about the plus 3, right? So the Bn is just 1 divided by n. All right, so the 1 divided by n, this is a harmonic series. And then based on my experience, as long as you wish to a harmonic series, usually the conclusion is conditionally divergent, usually. So harmonic series is always divergent. Can you prove that Bn is greater than or equal to An? So when n is equals to 1, we have 1 divided by 1. This is a 1 divided by 4. So we just prove that Bn is greater than or equal to An for n greater than or equal to 1, right? So since Bn is divergent, then what kind of number is less than or equal to divergence? So this divergence tells me what in here. So what kind of number is less, what kind of sum is less than or equal to divergence? So it can be a smaller infinity, which is a divergent, or it can be a real number, which is convergence, right? So we have convergence or divergence, and this one we cannot decide. What do we do when you end up in this situation? So when you end up in this situation, you have to use the limit comparison test. So for limit comparison test, we have to take the limit as n approaches to infinity. We have to do An divided by Bn. So that is limit as n approaches to infinity. 1 divided by n plus 3 divided by 1 over n. And then you take care of the complex fraction. So you end up with n plus 3 on the bottom and then n on top. So this one, when n approaches to infinity, how do you solve for that? So there are two ways to do it. So this one, if you just plug in the infinity, you will end up with infinity over infinity, right? So in that case, you can apply the L'Hopital's rule. You take the derivative of the top and then you take the derivative of the bottom. Or if you don't want to do L'Hopital's rule, the highest exponent in the denominator is 1. So you divide each term by n to the first power. And then after that, you have limit as n approaches to infinity, 1 divided by 1 plus 3 over n, the fraction goes to 0. Then you have 1 divided by 1 plus 0, so that is equals to 1. For limit comparison test, as long as the limit is greater than 0, then we say that they are both convergence or they are both divergence. So since An not yet. So since Bn is divergence because Bn is a harmonic series, then based using the concept of limit comparison test, we say that An is also divergence. Now, let's grab a highlighter. We just say An is divergence using limit comparison test, right? An is divergence. However, if you use the AST, the alternating series test, right here, alternating series test, we say that the series is convergent. So we have convergence and then we have divergence. Then what do we say? Then we say that overall, the series -1 raised to n plus 1 divided by n plus 3 is conditionally convergence. So for your own practice, here is what I suggest you to do. You can change n plus 3 to 5n plus 1. You will get the same conclusion. Okay, so you can try, change the n plus 3 to 5n plus 1. You will end up with the same conclusion. That is a really good practice. So now, let me move on to number 2. So number 2, switch to another color. Number 2, we have the summation. N goes from 1 to infinity. We have -1 raised to n plus 1 divided by the square root of n. So this is an alternating series, right? And the Bn is equals to 1 divided by root n. And then the next term is equals to 1 divided by n plus 1. So number 1, we have to show that Bn plus 1 is less than or equal to Bn. So when n is equals to 1, we have 1 over root 2. That is sure less than or equal to 1. When n is equals to 2, we have 1 divided by root 3. That is also less than or equal to 1 divided by the square root of 2. And then number 2 is you have to show that the limit of Bn is equals to 0. Alright, so we have limit as n approaches to infinity, 1 divided by n, which is 1 divided by infinity, then you get a 0, right? So that means the given series is convergence by what? By the alternating series test, AST, alternating series test. And then let's go deeper. So for the alternating series test, I just remove the alternating term, right? I just take it away. But what about taking the absolute value? So what if I take the absolute value of the given series? So that would be the absolute value of -1 raised to n plus 1 divided by the square root of n. So once you take the absolute value, that takes away the top, right? So the top is now 1. What about the bottom? Do we still need the absolute value? Is this still necessary? The answer is no, because as n goes from 1 to infinity, the absolute value, not the absolute value, the square root of positive is always positive. So that is just equals to 1 divided by square root of n, which is the sum of 1 divided by n raised to 1/2 power. And this is a p series. And the power is equals to 1/2. Since the power is less than or equal to 1, we say that the series is divergence. And then now, look at my conclusion. I have a divergence and a convergence. And then overall, what do we say? We say the given series is conditionally convergence. All right, so that would be the end of number 2. Let's take a look at number 3. Number 3, we have the summation n equals to 2 to infinity. We have -1 raised to the n divided by n times ln of n. Okay, so this is an alternating series. Then the Bn is equals to 1 divided by n times ln n. And then the next term, n plus 1, is 1 divided by n plus 1 times ln of n plus 1. So let's show number 1. So we have to show that the next term is less than or equal to the current term. And then when n is equals to 1, we have 1 divided by 3 times ln 3. That is less than or equal to 1 divided by, actually I cannot use 1 because that starts at 2. The reason is ln 1 is equals to 0. So we cannot have 0 in the denominator. So that must be equals to 2. And then 2 plus 1 is 3. Alright, so that one I got it right. And then the other one, I have 2 times ln2. So if you do a quick check on your calculator, this inequality is true. And then when n is equals to 3, I have 4 ln4 less than or equal to 1 divided by 3 ln3. So the first condition is true. And then the second condition is limit as n approaches to infinity of Bn, which is 1 divided by n times ln. This is 1 divided by infinity, so that is equals to 0. So number 1 is true, number 2 is true. We say that the series is convergent by the alternating series test, AST, alternating series test. Now, in the alternating series test, we just take the alternating term away. Now, what happened if I take the absolute value? And that is the reason why I picked this problem. So let's take a one step deeper. So now we are considering the absolute value of an, which is the summation of the absolute value of -1 raised to the n divided by n times ln. And then that is equals to the absolute value of what? The top is 1, right? The bottom, do we still have to use the absolute value? Do we still need that? The answer is no. If you consider the graph of ln, this is the graph of ln, right? And the x-intercept is 1, 0. And then since n equals to 2 or above, so when n is equals to 2, starting at this point and above, do we agree that the graph, the curve, is above the x-axis? So that means as n equals to 2 or above, we always get a positive term. And then since n equals to 2 to infinity, the n itself will be positive. That means overall, we do not need the absolute value. So n equals to 2 or above, then it's just 1 divided by n times ln. So this one, you cannot use geometric series. The P series is not going to work. So nothing works at this point. What can we do? We have to use the integral test. And that's why I picked this problem. All right, so for the integral test, we have to take the integral where the lower limit is 2, the upper limit goes to infinity of 1 divided by, let's just use x, and then ln x dx. So this one is a u substitution. We let u equals to ln x, du equals to 1 divided by x dx, and then x times du is equals to dx, and then we replace the dx with this piece. So what do we have then? We have a limit as t approaches to infinity from 2 to t. Oh, actually, we don't need to draw the integral anymore. So we don't need to draw the integral anymore. Actually, we don't need to go from 2 to t anymore. Just draw an integral because oh, this is x. This is x, not u. This is x. So when you replace the x with x times du, the x is in the denominator will be cancelled. Then we have 1 divided by ln x is u, and then du. So that is limit as t approaches to infinity. The integral of 1 over u is just ln, the absolute value of u, right? Where that goes from 2 to t. So the absolute value of u is just ln x. Okay, and then you do the fundamental theorem of calculus. So we have ln of ln infinity, right? ln infinity, and then minus ln of ln2. All right, so this will be ln infinity this is already an infinity, and then ln of this infinity is infinity, and then I really don't care what that equals to. So infinity minus a real number is just equals to infinity. So that means for the area, so if you look all the way to the right, this area is so big. So as a result, the area under the curve is very large, is infinity. What does that mean? That means using the integral test, the series is divergent. Using the integral test because the area under the curve is infinity. And then we compare the two conclusions we make. The first one we make is convergence, and the second one we make is divergence, in case you don't remember what I wrote up there. So we go up a little bit. Using the alternating series test, we have a convergence. And then using the integral test, we have a divergence. So that means overall, we say that the given series is conditionally convergence. So that is the end of this problem. Okay, so moving on to number 4. Number 4, we have a trick in the series. So number 4, we have the sum n goes from 0 to infinity, cosine n pi divided by n plus 1. Is this an alternating series? We have to find out. You don't see negative 1 raised to some power, right? So first of all, when n is equals to 0, we have cosine of 0 that is equals to 1. So that is positive. And then cosine of 1 pi, so which is pi, that is equals to what? That is equals to negative 1. We have negative. And then cosine of 2 pi, so that is back to the 0, 1. You have a positive. And then cosine 3 pi, you have a negative 1. And then that will be negative. So this is an alternating series. All right. So which means instead of using the cosine, we can rewrite the series as n goes from 0 to infinity of negative 1 raised to the n divided by n plus 1. And then I can perform the alternating series test. So Bn is equals to 1 divided by n plus 1. And then Bn plus 1 is 1 divided by n plus 1 plus 1. So that will be n plus 2. So number 1, we have to show that the next term is less than or equal to the current term. When n is equals to 1, we have 1/3 less than or equal to 1/2. When n is equals to 2, that is 1/4 less than or equal to 1/3. So that is enough of test. You don't have to test n equals to 3, 4, and 5. And then number 2, we have limit as n approaches to infinity of Bn, which is n plus 1, that is equals to 0, right? So that means overall the given series is convergence by the alternating series test, AST, alternating series test. What if we take the absolute value of the series? So what if we take the absolute value of the series? So that is the absolute value of cosine n pi divided by n plus 1. So since the cosine n pi, so what is cosine n pi give you? The cosine n pi, so for the cosine n pi, as n start from 0 and then you keep going, you get a bunch of 1, negative 1, right? And then 1, and then a negative 1. So once you take the absolute value of that, so you only just get a 1. So that means the top will be just a 1. So we have the sum of 1 divided by n plus 1. And then the absolute value is still there, right? But since that goes from 0 to infinity, so 0 or above, 0, 1, 2, 3, 4, 5, the bottom is always positive, then we really don't need the absolute value. It's just 1 divided by n plus 1. All right, so this is a 1 divided by n plus 1, and then we have to make a comparison. And then the an is equals to 1 divided by n plus 1. The bn is equals to 1 divided by n. And then this is a harmonic series. Harmonic series is always divergence. And can we prove that bn is less than or equal to an? So when n is equals to 1, we have 1/2, and then this is a 1. So that is a less than or equal to. So for the less than or equal to, we have a divergence. So that means on the other side, this can be a smaller infinity or a real number. So which one is correct? We don't know. So if you don't know, if you get stuck in this kind of situation, you have to move on to limit comparison test. For limit comparison test, you can just do the limit as n approaches to infinity, an divided by bn. As long as the result is greater than 0, then either they are both convergence or they are both divergence. So an is 1 divided by n plus 1, and then this is 1 divided by n. Of course, I don't want to skip the limit. And then you take care of the complex fraction. The bottom is n plus 1, the top is n. Solving this limit, since the highest degree in the denominator is 1, we divide each term by n. As a result, we have limit as n approaches to infinity, 1 divided by 1 plus 1 divided by n. Once infinity goes to 0, once the n goes to infinity, the fraction is 0. So 1 divided by 1 plus a 0. So that is just a 1. So since the result is greater than 0, either they are both diverge or they are both converge. So since Bn is already diverged, so if you look at the other side, then which one should I take? Then this one is diverged. Then we are not stuck in an either converge or diverge situation. So the limit comparison test tells me as long as one of them is converged, the other one must be converged. If one of them is diverged, then the other one must be diverged. So since this is diverged, using the limit comparison test, the result is greater than 0, then on the other side of the inequality, the AN is divergence. Right? So AN is divergence. Now, we have to compare two results. So the first one is AN is divergence right here. And then if you go back to the alternating series test, we have a convergence, right? So we have a converge and then we have a diverge. What do we say overall? We say that the given series, whatever that is conditionally convergence. All right, so that is how we do conditionally convergence. I know it's a lot of work, so you have to do your homework. You have to get enough practice to get everything right on the test. So that will be the end of this video. If you think my instruction is helpful, I picked the best problem to discuss, let me know in the comment section below. Subscribe to the channel, share the videos out for me. Trust me, it is worthwhile coming back to visit my channel. I will see you all in the next lesson. Signing off for now.